Hello, everyone. I'm Vivek Kwatra. I'm a research scientist at Google. I'm joined by my colleagues, Matthias Grundmann and Gregg. Today, we will tell you about the video stabilization technology that is available on YouTube, and also give you some insights on how it works and how you can use it to improve your videos. We'll show you some fun videos today, but along the way, we'll also try to tell you about the technical details behind the algorithms. To give you an overview of the talk, we will start by talking about video stabilization. Then we will give you some information about how we adapt that to work for mobile phones which have rolling shutter cameras. We will then take you through the life of a video as it goes through the YouTube stabilizer. And finally, we are announcing new features in the YouTube Upload API today that allow you to apply enhancements to your videos programmatically. So if you want to find out how to enhance your videos by adding some lines of code to your programs, then stay till the end, where we will show you a demo of that. So let me start by showing you an example of what we call a casual video. This video here is shot by somebody running with a camera strapped onto their head. So it's amazing that we have cameras which are light enough that you can strap them on your head while running, but that does not prevent the resulting video from giving you a headache. Thankfully, we have a solution for that problem. So this is the same video after it has been processed by the YouTube stabilizer. You'll note that the video is much less shaky, the camera looks much more stable, and the video is much more pleasant to watch. Here is the same video we're showing you side by side with the original on the left and the stabilized result on the right. One thing to note here is that to obtain this result, we only look at the pixels in the video. We only analyze the pictures. We don't have any information about the camera at this point. So how do you do this on YouTube if you want to stabilize your own videos? If you go to the watch page of one of your own videos, then you will see these extra buttons at the bottom. And one of these buttons is the enhancement button, which takes you to the Enhancement UI. And here you can apply different kinds of filters and effects to your videos. You can apply some fun effects. You can color correct by applying the autofix. And of course, you can stabilize. And once you click on Stabilize, you'll see this split screen viewer, which gives you a comparison between the original video and a preview of the stabilized results, so you can compare them and see if you like it. Note that at this point, the stabilizer is actually running live at the back end and streaming results to the user in real time, which is also why the preview is run at a lower resolution. The final video is processed at much higher resolution. And once you are satisfied with the video, you can go to the top right, where you have the Save button. You can save it by overwriting the current video ID, or you can save it as a copy, which creates a new video. And then the video is processed for stabilization. And then you go to your video manager or uploads page, where you will see a copy of the video appear, where you can play the video to see how the stabilized result looks like. So now we're going to the watch page of the stabilized video, and you can see the stabilized video here. We're also showing you the original video in the bottom left to compare the shaky result with what you get after stabilization. Now, of course, you can apply this effect on any video of your choice that you have uploaded, but we also try to help by offering some suggestions when we detect automatically that the video is shaky. So in this case, the blue bar at the bottom is offering a suggestion to the user to stabilize the video. You can click on the preview button, which again shows you the split screen UI, but this time right on the watch page. Again, you can compare the before and after. Note that as a user, you don't need to fiddle with any sliders or tweak any parameters. It's just a one-click stabilization solution. You just click Stabilize and you get the result. So now that we've shown you some videos, let's talk about how it actually works. So when talking about stabilization, one can broadly categorize into two main types. You can talk about in-camera stabilization, where you perform stabilization on the device while you're capturing the video. And when you do that, one issue is that you're only looking at the video as you're seeing it so far. You can't really see what's going to happen in the future, and that limits your ability to do stabilization. Also, you are limited by the processing power of the single device. The second approach is what we call post-process stabilization. This is where the video is already captured and encoded, and in our case, uploaded to YouTube. And we apply stabilization after the fact. So our stabilization is a post-process approach. And the advantage that we have here is that since we have the entire video at our disposal, we can do stabilization, for example, for the case where you are, say, walking with your camera, so you have these low frequency bouncing motions which you can't stabilize if you're just looking in the past. Also, you can distribute the computation in the cloud in this post-process setting, so you can use multiple machines to do much heavier processing than possible on a single device. There are three main steps in doing post-process video stabilization. We start by estimating the shaky camera path of the video. This is where you try to figure out or recover how the user was moving the camera while capturing the video. The second step is to smooth the camera motion, the original shaky camera motion, to obtain the stabilized camera path. And finally, you want to render a new video or a new movie from the viewpoints of these stabilized camera paths. So let's look at an example. Here we have a shaky video that we want to stabilize. And once we take it through these three steps, we have the stabilized camera path. Now you see this red rectangle here. This is our visualization of this new camera position. You can think of this as a virtual window that tries to move counter to the original shaky camera motion. In other words, it tries to stick to the background in the video so that you get a stabilized result. And to get the stabilized result, we essentially take the pixels within this rectangle and render them in the final video. But it's not really final yet. So what you see on the top is a stabilized video, but you also see these extra black borders around the video. And that's because when there is too much motion in the video, this virtual window overcompensates for it and goes outside the valid bounds of the video. And we don't really want that. That's sort of annoying to watch. So our solution here is what we call stabilization by cropping. And the idea here is that we can start with the same virtual window, but we shrink it a little bit to get rid of some of the contents around the border of the frame. And more importantly, we force this crop window to always stay within the bounds of the frame rectangle. What that means is that while you lose some content around the border, you always get pixels which are well-defined. So you get a final stabilized video which looks nice to watch. There is some content which is lost, but overall the result is better. So let's get back to the three steps I talked about, and we'll talk about them one by one. So let's talk about estimating the shaky camera paths from a given video. Now remember that what I told you was that we only look at the pixels within the video to compute the camera motion. So in this case, what I'm showing you here are these green dots, which are what we call local features. These are pixels which have high gradients in the x and y direction, which means these are things like corners. So if you look at the windows in the building, the corners of the window are good places to track or have local features. And that is because you can track them in the previous frame. By matching appearance, you can figure out where did each of these points come from in the previous frame. And once we have these features, we want to fit a camera motion to them. But there is one important point here, which is we don't want to treat all features equally. Since the camera motion only affects the pixel in the background, you don't want to take into account things like a person walking in the foreground, a car driving by. And we detect that automatically and figure out which features are background features, shown in green, and which features are foreground features. And those features are shown in red. And once we have these features that we can use for motion estimation, we finally compute what the actual shaky camera path was. At this point, I'll hand over to Matthias, who will tell you how we actually do the motion estimation.
Thank you, Vivek. Hey, I'm Matthias, and I'm going to talk about how we actually model the 2D camera path. So Vivek initially mentioned we start by having our original video, and we extract features at these gradient locations and track them with respect to the previous frame. So we get all these little displacement vectors. Now, in order to stabilize the video, we would need to stabilize the motion of each and every of these vectors, which is, of course, computationally quite expensive. So what we do instead is we try to summarize the overall motion of all these feature points with just a few numbers, what we call a motion model. Let's look at some of the motion models that one can employ in this setting. Well, the easiest motion model is that of a translation. In a translation, we only have translation x and y, or superimposed. So altogether, we're looking at 2 degrees of freedom, and if we use that to stabilize the video, we see it's still very shaky. And it's very shaky because there are some degrees of freedom missing, and that is the roll and the scale. So let's add that to our motion model. In this case, we have a similarity. A similarity has now translation x and y, as well as scale and rotation. So we're looking at 4 degrees of freedom. And if we use that to stabilize the video, we see it is not shaky, but it's still quite wobbly. And that's because there are additional degrees of freedom that are missing, and that is the yaw and the pitch rotation of the camera. So if we add that to our motion model, we obtain what we call a homography. So we have all the 4 degrees of freedom of the previous motion model, but now we also have skew and perspective degrees of freedom. Altogether, we are having 8 degrees of freedom here, and if we use that to stabilize the video, we see this is adequate to summarize the motion. So while we use this homography in our backend, for the ease of explanation, I will only focus on the similarity case, meaning 4 degrees of freedom over time, translation x, y, scale, and rotation. Now what we can do is we can plot the amount of each degree of freedom over time, and so we get a curve. So here, first we show you the translation x over time, the blue curve. The translation y, you see it's going up and down because that is a walking motion that we measure. We're looking now at the scale. You see a scale is going down because we're moving into the scene. And finally, the rotation, which is just wiggly, in this case, left and right. Now that we model basically the 2D camera motion with these 4 degrees of freedom over time, we can start stabilizing or smoothing them, which is the second step of our algorithm. So here we just show the translation x and the translation y. The original camera path is shown in red, and we're trying to approximate it with a stable path that is shown in blue. This is our result. So you see the stable path has some properties. When we started our project, we asked ourselves, what would be the property of a good stable path if a cinematographer would have captured it? Well, a cinematographer would use stabilization equipment, for example, a tripod. So you would have segments in your stabilized video that basically would have no motion at all, meaning a constant segment shown here in green. Or a cinematographer would have used a dolly or a pan where you have nice constant velocity, which reflects itself in a linear path shown here in yellow. You see the remaining arcs are basically parabolic segments, what we call ease in and ease out transitions, so that you can transition between the constant and the linear segments. And so our goal is now, given this original shaky path shown in red, to compute this stable path that is only composed out of linear, constant, and parabolic paths under one very important constraint, and that is the size of the crop window. When we look at the crop window, as Vivek initially mentioned it, if we have a very large crop window and we have to stay within the frame bounds, we can't really move around without hitting the frame border. So we can't really offset any camera shake. Now, the smaller the crop window, the more shake we can compensate for. And this reflects itself very nicely as an envelope around the shaky camera path that we measure. So the smaller the crop window, the larger an envelope around that shaky camera path. And now within this envelope, we're trying to find our stable path that will be only composed out of constant, linear, and parabolic segments. Let's look at a little interactive visualization of how you can imagine the solution works. So here we see our original shaky path in red, and now I will start increasing the bounds over time, and you will see how more stable the blue path will become. What's nice about our solution is it's robust to perturbations. If I move it around, as long as I'm staying within the envelope, the path doesn't change. I can use only constant paths to approximate the stable path, or I can use linear paths, in which case now I have these junctions here. I can also use just parabolic paths, which are very smooth, but non-zero throughout, or I can use a specific weighting that we employ in YouTube, which finds a nice sweet spot between these 3 types of paths, and is shown here. Now that we have the original path and we have the stabilized path, we can finally synthesize a new movie that looks like as if it would have been taken from the stable viewpoint, which is the last step in our algorithm. The stable path you can think of as this virtual camera that is shown here in red at this crop window. And so in this step, really all we need to do is simply apply a crop, and that will result in the stable video at the top. So let's look at some few more examples from YouTube. So here are some of the properties highlighted in a real video. if we can fit a tripod model, there will be no motion in the stable result at all. And now that the motion of the original camera picks up and the frame rectangle has to stay within the frame bounds, you see there's also motion in the stabilized result, but it's very nicely smooth, right? You have these constant velocity pans. Again, no motion at all in the beginning, nice tripod model, and now we have nice accelerations, constant pans, nice deaccelerations, and so the whole result looks very smooth, and a lot of the shake that was in the Y direction is gone from the result. Another example here recorded on a bike in Cairo, and so you see a lot of this high frequency perturbations in the Y direction, and it's completely gone in the stabilized result. The stabilized result really looks like just the handlebar moving very smoothly. In the second part, I would like to talk about an orthogonal problem, and that is rolling shutter removal. It's a little bit independent from video stabilization. To motivate the problem, let's look at the following example. Here we took a video that we recorded with an Android phone, and we deliberately shook the camera. What you see, it's not just camera shake. It's like these non-rigid, wobbly distortions that pose a problem here. And so our stabilization algorithm does rolling shutter rectification as well. And so we can take this original video shown on the left, and we can produce this rolling shutter removed result on the right. And you see it's still a video. There's a person walking on the bridge, but all the distortions are gone. Let's look at a little bit into the details why this problem actually exists. It exists because there are two types of electronic shutters. The classical shutter is that of a global shutter. In a global shutter, the image is captured at one instant in time. So we snap a picture or a video frame, then we move the camera slightly, we snap another picture, and we snap another picture. However, most cell phones use what is called a rolling shutter. So here the image is not captured at one instant in time, but one scan line at a time. So what you get is the camera is moving during the capture. And so instead of a rectified image, you get this skewed effect. And if the camera is actually vibrating during the capture, you get this wobbly result. If you compare global with a rolling shutter, you see the global shutter nicely rectified, the rolling shutter, all the houses are skewed. And so when you plot the scan lines over time, how they get recorded, what you basically see is they are slanted, they are offset. The image is not captured at one instant in time anymore. Now, if you don't account for this, here I show you original video taken from a helicopter. You see all these rolling shutter distortions. And so in our initial launch of the YouTube stabilizer in 2011, we didn't account for rolling shutter yet. You see the result is more stable, but there's still all these wobbly distortions that remain. So how can we solve this problem? Something that makes the solution more challenging is that the speed of the readout varies across cameras. So for more high-end cameras, you will basically have these blocks are a little bit more aligned, and then if the cameras take longer, you will basically have a more slanted arrangement. And at YouTube, we only have the video. We don't know which camera, which setting, or which scene you recorded. And so our solution is calibration-free. And the idea is basically, instead of using one motion model, we use multiple ones. We use one that describes the motion of the top third of the frame, and then the camera moves to a different configuration. So we have a motion model for the middle frame, and we have a motion model for the bottom frame. We actually use 10 motion models and a little bit of interpolation, but this is like the simplified explanation of it. When you use this new mixture model to account for the camera motion, you can take this video, and then after our launch of rolling shutter removal in YouTube, we produce the following result. Nicely accounts for all the wobble distortions. Here's another video from CitizenTube, also recorded on a bike. CitizenTube is a crowdcasted news site, and so you see a lot of wobbly distortions in this case. And here's our rectified and stabilized result. And one more time, side by side, for better comparison. In the next part of the talk, I would like to give you a little overview what's actually happening behind the YouTube stabilizer that uses those two algorithms to produce the result, or some of the results we earlier saw. So here, just to motivate it or to remind you again, this is the Enhancement UI, where we detect that your video is shaky, so we offer users a preview button. You simply click on the button, and then we compute the stabilized result in real time and stream it to the user. We also detect that this video, in addition to video shake, was corrupted by rolling shutter, so we do rolling shutter rectification in real time on top of the stabilization. Let's look at what's going on behind the scenes. So we have our video here, and we start by clicking on preview. In the moment you click on preview, a server request is sent to our cloud to start the stabilization. The first step is to compute the camera path. Remember, this is just extracting the features, getting these little displacement vectors, and then getting the original 2D path. Because we only look at frame pairs, this is highly parallel. So we can simply distribute this across many, many machines. Once we have the 2D camera path, we can then send it off to our stabilization engine to compute the stable camera path. There's a little addition here, and that is I haven't talked about what's actually the size of the crop window. And we can do this dynamically, and we'll look into this in a bit. In the last part, once we have our stable path, we can apply the cropping. Again, this is done on frames, so this can be done in parallel. And then in the end, we live stream the result to the user. I'd like to highlight that this pipeline can be run independently. So the actual throughput of our system is so high that we can compute the stabilization and rolling shutter rectification on low resolution video in real time and stream it to you. I would like to highlight two things of this pipeline in more detail. First, the auto crop. So I haven't really talked about what is the size of the crop window. What we would like to do is we would like to maximize the crop window so that we can offset most of the shake, but also give you most of your image content. Don't crop too much. And what we do is we do it adaptively. So what we see here is we start with a crop window that is rather large because we don't have a lot of shake in this segment of the video. And now the user will basically start shaking the camera more, and so the crop window now adaptively contracts over time to account for this. And here the user now will stop shaking the camera as much as before, and so now the crop window will smoothly and adaptively expand over time. So we measure the amount of shake, and based on that, we size the crop window. Another challenge that we face at YouTube is that videos are often pre-composited in some other software. So for example, you have overlays. Overlays are not part of the video, and so if you don't account for that, what happens is these overlays dance around. Right? And the user that's not familiar with the video will see this. It's not a satisfactory result. So what we do is we detect if major overlays are present, and in that case, we don't stabilize those parts of the video at all to avoid that. And once the overlay fades out, we detect it and then nicely transition into the stabilized result. So since we launched our system, we have gathered user responses, and in particular, two of them are when we detect that a video is shaky and we suggest stabilization to the user, how many actually accept this suggestion, and of those that do, how many keep the stabilized result. And the responses collected over millions of videos is 55% accept stabilization after we suggested that the video might be shaky, and of those that do, 95% keep the stabilized result. So only 5% go back to the original because they didn't like the stabilized result, or the stabilizer might have not performed that well. So far I talked about stabilization of videos. But what we can do is we can actually do stabilization of photo bursts as well. And this is deployed in the Google Plus Auto Awesome feature that you heard about in yesterday's keynote. So while there are many other algorithms used in the suite, the stabilization is used prominently in three of them. That is Google Plus Motion, Google Plus HDR, and Google Plus Smile. In Google Plus Motion, what we do is we take a photo burst and we create this animation shown on top out of it. And so what is desirable here is basically to nicely align the background, get rid of all the alignment issues, so that the foreground really pops. Right now that the background is aligned, the foreground object really comes out in this animation. We also use it in Google Plus HDR. When you take an exposure stack when you use your camera in bracketing mode, it's rarely the case that you use a tripod. So there will be a little bit of camera shake. And so what we do is we run the stabilization up front so that the images all nicely align before we apply the HDR, which then reduces ghosting. What we can also do is we can align faces. So if you take a photo burst of your family, we can align the faces and then create a new composite that hasn't been taken by you, where we try that all the faces that are shown are smiling. And so here are some more examples. You see the animation that we created, a foreground, a waterfall, and finally the smile where we create this new canvas. And with that, I hand it over to John.
Thank you, Matthias. My name is John. I'm an engineer on the video editing team at YouTube. And just for the last part of our talk, I'm going to talk to you about a new feature that we're launching today, which allows developers to take advantage of the stabilization feature in a new API for enhancing uploads. So here you see the user-facing enhancement API. There's a wide variety of options, including these stylized filters, trimming your video, color correction, and stabilize. And what we've done is taken the two most popular features of enhancement, the stabilizer and the autofix, which we could talk in a lot more detail about, but it's basically a histogram stretcher that's temporally smooth over the video, so it improves the contrast and colors in pretty much any video. We've taken those two features and added them to the YouTube v3 API, so any application that uploads to YouTube can add, with just a couple lines of code, instructions to apply these effects after the video has been uploaded. So I'm just going to walk through a quick demo of it. So this is just running an app engine. You can imagine any application that's capturing video and uploading it to YouTube. This one's just called John's Uploader. So let's upload this video, which didn't work, but it would look like this. So this is just playing the raw file in the app, so in the camera, for example. And we're going to publish this to YouTube. Just check a few boxes, publish it, and here it's been published. You see a message that it's processing, and also that the video edits are being processed. So while we can do the low-resolution preview nearly instantaneously, processing a higher resolution does take a few minutes, but I've happened to already uploaded a copy of this video. And you can see the stabilized version on YouTube versus the shaky version in my app. So how did I do this? This is using the YouTube v3 API, which is where this new feature is now available. It's just two Boolean parameters on the video's insert instruction called auto levels and stabilize to apply each of those effects. These are simply Boolean parameters. As we've already described, we have pieces of the technology to automatically compute the optimal parameters, so you don't have to worry about sliders or complicated controls. The edits are all performed in the cloud, so again, you don't have to worry about implementing these things on a device, which also allows the user to revert back to the original version if, for whatever reason, they're not satisfied. So here's a code sample. This is using the API library for Python in App Engine. So this is just a request setting the body and title, description, and the bytes of the upload. And it really is just 2 lines of code added to this request. This is actually taken from my app, so it's grabbing the values of those checkboxes and setting stabilize and auto levels parameters. And that's really as easy as that. So this is available today. We hope app developers find it useful. And with that, it's the end of our talk. So just to summarize, we talked about the video stabilization technology, which compensates for a lot of the common problems with casual video, including rolling shutter. And then the Enhancement API, which allows developers to add these corrections right in the applications. So thank you for coming. One last example to leave you with. And if you want to scan this QR code, you can rate the talk. But with that, we'd be happy to take any questions. Sure.
Hi. Well, I have really enjoyed using the stabilization. So I'm using a GoPro camera, and which I imagine a lot of users are for kind of high action photography are using a camera like that. That has a very wide angle lens, and I think the model that you're using for stabilization doesn't account for the kind of distortion that you'd get in a extremely wide angle lens like that. So you get some very bizarre kind of distortion effects that propagate across the field of the virtual camera as you're moving it. And I was wondering if you have any plans to, or if you're aware of that, and like your plans to try to detect different lens models to try to correct them more accurately.
Just want to talk about that?
Yeah, so yeah, we are aware of that there is a problem with GoPro cameras because of the wide field of view. This is actually a GoPro camera, and if you use it in the more narrow field of view, it works decent, but the wide field of view is a challenge. There's a challenge to basically detect which setting you use just from the video file. But yeah, we are aware of the problem, but it's so far has been a difficult problem to solve.
I have another question if nobody else is coming
Sure.
back up to the microphone. So I've also been doing photography mounted on a quadcopter, so there's often a kind of a form of vibration, very high frequency vibration in the camera, and I don't know, is your rolling shutter algorithm able to deal with something like that, or maybe detect a certain frequency of vibration to try to more accurately get rid of the rolling shutter effect?
So our rolling shutter algorithm detects rolling shutter. Now the question is, of course, how crazy is the distortion? Because we do it automatically, we calibrated it for the most common use cases, so we can work on vibrating patterns from helicopters a little bit, from driving cars. But if it gets too crazy, if simply the camera motion just becomes too large during the capturing process, it might not always work.
Yeah, well, I wonder if it's also like the blades of a small quadcopter, they might be, like a, I don't know, 80 hertz or something, so like maybe a higher frequency range than you're used to, maybe detecting automatically as,
Correct.
Then you might not be detecting the, how to actually get rid of the rolling shutter in that case.
Right, for those specialized cases, we might not always do a perfect job, because we strive basically for this one-click solution with the absence of any sliders, and so that might not be the best use case for that.
Okay, thanks.
Thank you.
Just to add to that, it's a calibration-free approach. So we're doing it on YouTube after it has been uploaded. So we don't necessarily know always which camera is used to compute that. So we need to know, or we need to compute this information just based on the pixels. So we do as much as we can, but we can always strive to improve it.
Hi, so as you talk, you're using the software method to detect the motion of the phone or the camera, right? So is there any possibility in the future that you can upload your motion vector with the video to the YouTube so that you can just better stabilize the video?
John?
It's a good idea.
Yeah.
It's I think it's something that we think about, but right now it's too complex, I guess, and we want to have a general purpose solution that works even when we don't have that information. So having the extra information would probably help. It's just a matter of working it into the system.
Right, and another question is that so you upload the 1080p video, and after the cropping, and so the video becomes smaller, but on the YouTube, so we still are watching the 1080p video, so the quality drops dramatically. So why we are still watching in the 1080p definition? Because it's not the 1080p definition anymore. So.
Right, we do scale the video back up to the original size after cropping. So it appears to be the same resolution, although you're right, there is a bit of a loss of actual image data.
We do some sharpening on the video after scaling it, but yes, you do lose resolution because you're cropping it.
So that leads me to what I was going to ask about effect this has on compression quality, because presumably then the motion estimation that the codec is doing is much simpler because you've moved it into a more 2D domain and out of the domain where the codec tends to fall over when you are doing that to it.
Correct.
Do you notice that? The difference between the codec performance is improved before and after this? If you measure, if you've measured that.
So I think in principle, definitely having less shake in the video should give you better compression performance with lower bitrate. It would be interesting, if you would have actually the raw video available.
Right.
We already have the encoded compressed video, right? So it might not be a really benefit for us.
It depends what it's shot with. Yeah. If I uploaded an uncompressed video, but yeah, most people already give compressed.
Right. So there might be some benefit.
So that leads me to another couple of questions, which is, those videos have motion vectors in, but they're probably really bad because they've been estimated by a camera. So presumably you ignore those and just look at pixels. But do you look at, once you've done your coplanar recomposition of the thing, you could potentially reconstruct better pixels across the motion from the fact that there are multiple shots of the same piece. So if there's some bit that's been squished into low frequency because of the DCTs, you could actually construct better pixels from a frame before and after. I'm assuming you haven't looked at that, but is that something you've considered looking at?
That's a good suggestion. We haven't necessarily looked into that because we were just focused on in the stabilization. That's sort of an additional enhancance you could do. You could think of that as sort of super resolution or sort of.
It's sort of like HDR. It's like but for sharpness. Yeah.
No, definitely, that's a good suggestion. Something that can definitely enhance a video, but we haven't.
And that takes me to the sort of third iteration of this thought, which is grumbling about codecs. The codecs all have these stupid small two-dimensional squares moving around in space models, whereas you're constructing a much more fluid 6 degrees of freedom model for how the thing is moving, which implies you construct a different kind of codec that plays better with the GPU, where you say, okay, if we actually understand how the camera's moving, we understand what will be good triangles and textures, we could feed something through to that. And people are starting to do research on codecs that are written entirely in JavaScript and WebGL to take advantage of that. I think this stuff will be great to feed into that, because if you start from a game or something where you've already got the GL surface, this is straightforward. But you seem to be doing a fairly good job of saying, okay, this should be textured, and then we could decide where the tri-meshes go depending on how coherent they are. There's probably, this is the beginning of a really interesting new kind of codec.
Thank you. Yeah.
Session. Thanks.
So kind of two questions. When you're reconstructing the new smoothed camera path, there seems to be a lot of parts where you have kind of chosen to reconstruct it so it looks like a professional photographer, or so it follows particular, as you say, to keep a still image of particular parts. I was wondering how you kind of optimize within all of those constraints, because it seems like quite a big optimization problem to be doing in real time.
So we haven't talked really about the details, but if you're familiar with solving systems, usually people use something like a least square solver. This boils down to a L1 solver. We have a little bit of the math details, or actually all the math details, up on the Google Research blog, and wrote a paper about it. So if you're really interested on how that constrained solution works, how you set up the equations, and how you find the solution, you're more than welcome to check out that paper.
And the other question was, is there any open source code for any parts of this, apart from the stuff that's commonly done, like motion,
Well, there is no open source, but there is this new API, and we encourage you to use that, so you can leverage also this whole distributed pipeline that we set up to do this in a highly scalable and performant way. Thank you.
Hey, really cool talk. I was just curious, it sounded like you do linear segments with parabolic transitions between them. Have you uploaded like real Hollywood videos just to see what real cinematographers do as far as their curves? Or do different cinematographers have slightly different curves where you could apply it in the style of this person or that person? Have you done any of that sort of analysis even just internally? Or?
It's a great suggestion. Basically, I like to stretch a point. What we're doing here is we're trying to mimic certain moves cinematographers do. Right, and so these are really just a constant linear parabolic arcs. Cinematographers in many settings, there's a very artistic note to it. So it's a good suggestion, but I think the space of camera motions would be much more complex. And so we're not doing exactly what a cinematographer would do, we're just mimicking these certain moves here.
Yeah.
Thank
Cool
you.
stuff, thanks.
Thank you.
Any more questions?
Well, like following up on that last one, you talked about dolly tracking and tripods.
Yes.
But there is a whole bunch of other motion things. There's Steadicam, there's Luma cranes and things like
Right.
that. And they will have different characteristics, so you could probably extend the model a bit there. But the other fun thing would be to say, if you've got a movie that's using this for effect, if you put the Blair Witch Project through this, you may get a very different movie.
Correct. Thank you. Okay.
All right, thanks
Thank you
everyone
very
for
much.
coming.
Thank you for coming.